Okay, so this is going to be a relatively short video because I just want to discuss what limit of a sequence is, because this is going to be a pretty small idea now, but it turns out to be a huge idea once we start talking about sequences and series later on in calculus. So it says, let f of x be a function such that the limit of this function as x approaches infinity is some value L. If you have some sequence, which we'll call a sub n, if we have a sequence that can be written in terms of that function, then for every positive integer n, then the limit as n approaches infinity of that sequence is going to be that L value. All right, let's pause for a second because that sounds like a lot, but here's all we're saying. All we're saying is if you have some sequence, which we'll call a sub n, if that sequence can be written as a function, and if that function has a limit at infinity, then guess what? That sequence will have some value that it approaches as the number of terms gets larger and larger and larger. All right? Again, that still might not fully sink in, but let's take a look at a particular sequence to really make sense of this. Suppose you have some sequence, and that sequence is defined by a sub n here. Okay, so there's your sequence. Now, if we have some sequence and it's defined as being 1 over 2 to the n, what does that sequence look like? Well, I've written it out for you. Here's my sequence. When n is equal to 1, I've got 1/2. When n is equal to 2, I've got 1 over 4. When n is equal to 3, I got 1 over 8, and so on. You get the idea, right? So let's take a look at the sequence here. Can we think of that sequence as a function? In other words, can we write this as f of x is equal to, instead of 1 over 2 to the n, is 1 over 2 to the x. And you're not going to need to do this every single time. I'm just doing this right now so that you can kind of understand what I'm trying to say up here. Well, think about this. What is the limit of this function as x approaches infinity? Since we just talked about limits at infinity, what's going on here? Well, as x gets closer and closer to infinity, as x approaches infinity, think about what's going on with our denominator. Our denominator is going to be huge. And we know from the limits at infinity theorem that any constant divided by a value as x approaches infinity, in this case here, this is going to be equal to 0. So what we see here is that as x approaches infinity, f of x approaches 0. There's our L value. So if this sequence that we were given up here can be thought of in the same way of this function, all I did was just rewrite and replace the n with an x. If that sequence can be thought of as a function, and if that function has a limit at infinity, that means this sequence here is going to approach what? It approaches 0. Therefore, we can make like a concluding statement here. We can say, therefore, the limit as n approaches infinity of 1 over 2 to the n is equal to 0. All right. Now, this was just an example just to demonstrate this idea. There's really not much work that you're showing here. But all this is to hammer the point that this particular sequence here, as the number of terms increase, as the number of terms approaches an infinite number of terms, we see that this sequence, and it's pretty obvious to you just by looking at the values, think about what would happen after 1 over 32, 1 over 64, and so on. This sequence will approach a unique number. And when a sequence does approach a unique number, it is said to converge. Okay? Convergence means a sequence approaches a unique number, a specific value. In this case, that value was 0. A sequence that does not converge to a unique number and does not have a limit is said to, let's do this in a different color, diverge. Okay? A sequence diverges if it does not approach a unique number, which means its corresponding function does not have a limit at infinity. Okay? So this particular sequence does converge, and there are many other sequences that do not. Okay, let's try an example with a slightly more difficult function, but still not that bad. Okay, let's find the limit of this sequence whose nth term is written as such. And again, what we're effectively asking ourselves is, does this have a limit? If so, this sequence is said to converge. And if it does converge, what value does it converge to? Or what's the limit? So before I do any work with this, I've got this rational looking function that looks a little complicated, so I'm going to clean it up just a little bit. I got an n up here, and this I can write as n squared. And other than that, I'm probably going to have to rewrite this. So this is 5 times n plus 1, 2n plus 1 over 6n squared. And let's just go ahead and expand it. And you know what? I'll just go ahead and start writing my limit statements here. So we'll say the limit as n approaches infinity of a sub n, our a sub n term, is the same thing as the limit as n approaches infinity. And let's go ahead and expand that numerator now. So we got 10n squared plus 15n plus 5 over 6n squared. And you know what? Let's create a little space. Let's just move that down a little bit. All right, here we go. So now that we have that, well, I want to be able to start splitting this up into terms so I can apply the limits at infinity theorem. So let's write it as such. Let's write this as the limit as n approaches infinity of 10n squared, and I'm just going to highlight this as I go along. 10n squared divided by 6n squared. Well, 10n squared divided by 6n squared, 10 divided by 6 is 5 over 3, and those n squares are going to divide out. Okay. And then let's go ahead and do 15n divided by 6n squared. Well, that's going to, 15 divided by 6 is 5 over 2. And we've got an n left in the denominator. And then finally, let's go 5 divided by 6n squared, which is going to be 5 over 6n squared. It's just that. Okay, don't need that anymore. All right, so now we can just find the limit of each one of these terms. Well, the limit of 5/3 as n approaches infinity is still going to be 5/3. And for this, think about what's going to happen. What's going to happen with these terms? That's going to approach 0. That's going to approach 0. And so the limit of this particular function is 5/3. And again, what does that mean about our sequence here? It means this sequence does converge. And what value does it converge to? 5/3. Okay? And trust me when I say, if you're planning on taking Calc BC, you will discuss this way more in depth. But this is just a nice kind of sample of what's to come.